Alright, it's time to start balancing chemical equations. The reason why we balance is to support the law of conservation of mass. That says in a chemical reaction, mass is never created or destroyed. So all atoms on my reactant side need to be present on my product side. The idea is just that the existing atoms are somehow rearranged to form new products, and those new products have different properties. So maybe we'll say atoms are rearranged, but they all must be accounted for. I cannot create or destroy atoms. So on a small scale, like on a particle level, here might be a way of interpreting this equation. We've got two molecules of water, two individual water molecules, where the oxygen is this bigger particle, and the hydrogens are the small ones, H2O. Two individual molecules. Now again, in a previous video, we also said that on a larger scale, you could think of this as a ratio of moles, but I'm not going to draw 1.2 times 10 to the 24th water molecules. That might take me a little while. Okay, so if we add energy, this is endothermic, we can decompose the two water molecules, but all existing atoms must still be present on the product side. So if I start with a total of 4 hydrogen atoms, 1, 2, 3, 4. They're still present. 2 molecules of H2 hydrogen. The 2 oxygen atoms are still present. 1 molecule of O2 diatomic oxygen gas. On a particle level, that's kind of what those coefficients mean. Now let's look at balancing some real equations. And I'm hoping that this is something that you have done in the past. Maybe not in the recent past, but in a previous life you've balanced chemical equations. We kind of mentioned that the only thing you can do is change the coefficients. You cannot change subscripts to balance a chemical equation. So for example, let's look at this first one. KClO3 produces KCl plus O2. Well, yeah, diatomic oxygen gas, that's its elemental form. You can't just erase the 2 by oxygen and make that O3. Oxygen gas is not triatomic, it's diatomic. I guess along the same lines, you cannot erase this 3 and change it to a 2. That's not the correct formula of the original compound. That's potassium chlorate. So if I need to balance this, I get it. It looks as if I destroyed an oxygen atom, and I can't do that. We'll use coefficients. So right now, potassium is balanced. There's 1 atom of potassium on both sides. There's 1 atom of chlorine. But then to balance the oxygen, I have a 3 and a 2. So you're probably looking for a common multiple. Try 6. So if I put a 3 here, 3 times 2 would give me 6 oxygen. Then if I want 6 oxygen on the reactant side, my only option is to go all the way out in front. 2 times 3 is 6. However, in the process, you also doubled the potassium and the chlorine. By putting that 2 out in front, you doubled everything. Oh, well, not a big deal. 2. That's why they call it balancing. You may need to work these back and forth until you get the same amount of atoms on both sides. And I promise they will work. Eventually, you're going to get so good at balancing these equations. Now, here's a little trick. Something like 2. What could potentially make 2 annoying is the fact that there's oxygen in all 4 particles. Both reactants and both products have oxygen. And so you want the total number of oxygen to be the same on both sides. See if that oxygen is coming from a polyatomic ion. So for example, like here's nitrate, NO3. Then nitrate stays NO3. If you have a polyatomic that stays together, you could just balance it as a group. And then I could just say, well, here's oxide, here's oxide. I'll balance those guys together. Otherwise, you're going to end up having to add so that the total amount is the same on both sides, and it works, it'll be fine. But this might go a little quicker. So watch what I can do. On my reactant side, I have 1 atom of sodium. On my product side, I have 2. I want 2 sodium, I have to go all the way out in front. That gives me the 2 sodium. I'm going to think of this as 2 nitrate groups. Well, look at this. There's 2 nitrate groups. Well, I don't mind that. 1 lead, 1 lead. Well, what do you know? There's 1 oxygen and 1 oxygen. It's balanced. Now, you can leave those blanks blank. You don't have to fill them in. You could put in a 1 if you wanted to, but I usually just leave them blank. Now, that wasn't so bad. Now, here's the difference. When I say that I have 2 NaNO3, it means that I have 2 separate molecules that maybe we could just kind of write as if they looked like NaNO3. And then I have another one, NaNO3. Kind of bigger than the first one, that's fine. When I say that I have lead nitrate, then I have something like this. Lead nitrate, nitrate. By putting the 2 out in front, it means you have 2 individual molecules of sodium nitrate. Each molecule has a nitrate group. So I have 2. If I have something like the lead nitrate where the 2 is a subscript, I have 2 groups of nitrate, but now they are directly bonded together. It doesn't matter. Both are 2 nitrate groups. It doesn't matter if they're in separate molecules or if they're together in the same molecule. It still counts as 2 groups of nitrate, and it does balance. So now let's say I was doing 3. And I got 1 silver, 2 silver. All right, I want 2. The 2 goes out in front. I got my 2 silver. Now I got 2 iodine. Ooh, dang. I got 3 iodine. Okay, well somehow you're going to have to make these guys balance. Often you're looking for a common multiple. So maybe 6. I could do 6. Whoopsies. Hello. To get 6, why don't I just put a 2 there? Difficult math. There, 2. That's better. Now, could I get 6 iodine? Sure. I mean, now I'm going to have to just put in a 6. Well, let's see if we can do this. 6. Okay, now, that gives me 6 silver. So I'm going to have to go back and rebalance the silver. 3 times 2 is 6. And again, that's why they call it balancing. I thought I had it, but then when I balanced another element, the iodine, I screwed up the silver. So we go back and forth. Look what happened. I need 2 iron, 2 iron, 3 groups of CO3 carbonate. What do you know? 3 3 groups of carbonate. It works. They are meant to work. They will balance. I promise they will balance. You just have to work them from side to side. That wasn't so bad. So you might get a little larger coefficient. It's okay to have a 6. It doesn't just have to be 1, 2, 3. Now if I get something like 4, it kind of looks like 2 in the sense that there's a lot of oxygen. But the oxygen's not really coming from the same kind of particle. It's not coming from a polyatomic or the same kind of ion. It's all a little different. In number 4, I have no choice but to just balance the total amount of oxygen. Now I'm probably going to leave that to the end, and I'll hope that by balancing everything else, maybe the carbon ends up being easier than I expect. So I need 2 carbons on both sides. 2, 2. There we go. 4 hydrogen. To get 4 hydrogen, I'll go 2 times 2. And now the oxygen. 2 times 2 is 4, plus another 2. My product side has a total of 6 atoms of oxygen. On the reactant side, I don't really want to mess with this first carbon compound. I mean, I get it. I could put a coefficient in front. I could put a 2 there, and that could get me 6 oxygen. But then I would screw up my carbon and my hydrogen, and right now they're balanced. So instead, I'm going to count this as 2, and we'll put the other 4 on the O2 oxygen. So now here's 2 and 4 for 6, 4 and 2, 6 total oxygen, without having to go back and rebalance the carbon and the hydrogen. See, they're not so bad. And now obviously if you have something like 5, now I'm back to polyatomics. There's tons of oxygen, but look at it. SO4 sulfate, SO4 sulfate, CO3 carbonate, CO3 carbonate. The oxygen is part of a polyatomic and it stays the same on both sides. So you really can think of it as just one group. Now watch this. Zinc, zinc, sulfate, sulfate. 2 lithium, 2 lithium, could it be? Carbonate, carbonate. It's balanced. It's done. Well, that wasn't so bad. In this sense, you can just leave all the little blanks blank, and that would be assumed to read as a 1-to-1 ratio. I'm totally fine with that. Or put in 1s if you want to. Or here's something like 6. I think the more you practice, these really aren't so bad. There's a lot of times where people will say, yeah, I sucked at this when I was in freshman physical science or biophys or whatever. And then all of a sudden they just get it. I just get it now. Vanadium 2. Vanadium 2. Oxygen 5. I need 5 oxygen. Calcium 1, but now I have 5. Awesome. Sulfur, I got 5. And what do you know? 5 sulfur on both sides. It's done. So I might suggest, at this point, maybe pause the video, try the last few, and then bring it back and see if you're getting them right. The more you practice, I promise, these things do balance. They're meant to balance. Here's the last couple. These aren't so bad because the formulas are given to you. So you don't have to worry about something not balancing because you don't have a formula, correct? Number 7 is already balanced. 1 manganese on each side, 2 groups of nitrate, 1 beryllium, and 2 chlorine. It's done. Number 8, I thought of phosphate as phosphate. It stays as a group. So by putting the 3 out in front, I have 3 silver on both sides, 3 bromine on both sides, 1 gallium, and 1 phosphate. Sometimes number 9 causes a few issues. People notice the 2 polyatomics on the reactant side. Like, oh, sulfate, SO4. And they see it right away on the product side, SO4, sulfate. But then initially, they don't see where'd the hydroxide go. I've got some boron hydroxide. Where'd it go on the product side? So they're not quite sure what to do with those oxygen. Because again, there's oxygen all over the place. Well, I mean, this will balance whether you think of polyatomics as a group or you split them into the individual elements. One trick, water can be thought of as hydrogen hydroxide. Hydrogen is always the sign of an acid, so that H2SO4 is acidic. It's actually sulfuric acid. Hydroxide is always the sign of a base, so that boron hydroxide is a base. Well, we say water is neutral because it has 1 hydrogen and 1 hydroxide. If you want, you could write water as HOH. That's where the hydroxide is. The hydroxide is kind of bonded with the hydrogen from the original acid. And it does form water, and often we just write it as H2O. But you could split it if that helps you balance. There is a total of 6 and 6, 12 hydrogen on both sides. There's really 3 sulfur. There's really 2 boron on both sides. And then the oxygen. Yikes! You've got 3 times 4 for 12 oxygen coming from the acid. Here's 3 oxygen in the base. There's my 3. Times 2 would give me another 6. You do have 12 oxygen. And then here's another 6. So it does balance. And number 10 balance is really slick. 1 iron, 2 silver, and 2 groups of nitrate. So hopefully this kind of rings a bell of something that you have done in the past, in a former life. I'm pretty confident that you have balanced equations, and it'll just take a little practice so that it comes right back to you.